Okay, so we've been talking about the implementation of OSPFv2 in a single area. We've discussed the network statement, setting up the routing process itself, etc. One of the other things that we have to take into account is providing OSPF with useful information for its metric. Now, the metric for OSPF is cost. It is a cumulative cost of all the exit interfaces between point A and point B for all possible routes. And what OSPF does when it's calculating the SPF tree is it figures out which available route has the lowest cost. Now, if you have an older network with, say, slow Ethernet and some T1 lines and some BRI, some basic rate ISDN, and some really slow, say, DS0, that would be your 64 kilobit serial line down here. That's a DS0, digital signal 0, the basic component of BRI, ISDN, PRI, ISDN, and T1 and T3. Basically, an ISDN line or a T1 or T3 is a collection of DS0 channels. Anywho, so if you have an old network like that, you can use your fast Ethernet as your reference bandwidth. Your default bandwidth in megabits per second, in bits per second, is essentially set at 1 megabit per second, which is slower even than slow Ethernet. Now, on a modern network built predominantly with fast Ethernet and gigabit Ethernet interfaces, the fact that you're using the fast Ethernet speed, 100 megabits per second, as your reference bandwidth has an unfortunate consequence, which is to say that until you tune that to use a more appropriate default reference bandwidth, it will treat a fast Ethernet interface and a gigabit interface and a 10 gigabit interface as though they are functionally equivalent, when they most certainly are not. So what we need to do is adjust that. And we'll talk about that, how that works with the reference bandwidth. So, as I said, OSPF accumulates cost. So let me move myself here. Okay, so OSPF accumulates cost. So your cost, say, for example, from LAN R1 to reach this LAN over here, from this LAN over here, if you've got a cost of 64 for this T1 line here, and a cost of 1 for this gigabit interface here, your cost is 65, which shows up right here in the show IP route statement. You'll have your, as usual, you have your source, your network, your mask, your administrative distance, your metric, and your interface and your exit interface and all of that. If you do show, now another fun thing you can do with show IP route, which you probably haven't seen before, you can tell the routing table to give you the lookup for a specific network by punching that network's interface, or rather address, in with show IP route. Say, instead of show IP route OSPF or show IP route static, you can force it to basically give you its routing table, the results of that routing lookup. So show IP route 172.16.2.0, you'll see using OSPF10 with a distance of 110 and a metric of 65. It's an intra-area, so far so good. You'll see its update, you'll see its routing descriptor block, etc. It's a very useful thing to have in your back pocket. If you're trying to check how the router is deciding how to route to a specific interface, you can actually tell it to do just that, rather than trying to read the routing table. Now, you need to be able to read a routing table. That is a very important skill to have. But if you want to double check what you think it's doing with what it's actually doing, you can do show IP route and then provide it with the network address. So I mentioned adjusting that bandwidth. What we can do is use the auto-reference bandwidth command to change the default bandwidth from, say, 100 megabits per second to a gigabit per second. Say, for example, if you've got all of your routed interfaces in your network are at least a gigabit, have at least a gigabit worth of bandwidth. Maybe some of them are 10 gig E or 40 gig E or some other flavor of gigabit Ethernet. You can change the auto reference bandwidth command and tell it to do that. The thing to note here is that when you do this, what you're going to do is give it megabits per second. So a gigabit interface runs at 1,000 megabits per second. A 10 gig E interface runs at 10,000 megabits per second. So as you can see from these two tables, with the auto cost reference bandwidth 1,000, your 10 gig E has a value of 1. Your 1 gig E has a gig E has a value of 1, and also your 10 gig. And if you have a lot of gig E but not so much 10, that's fine. Now, if you really do need to compensate for the fact that you've got 10 gig interfaces and 1 gig interfaces, then you crank that all the way up to auto cost reference 10,000, and it will treat the 10 gig interface as a cost of 1. Your gigabit interface has a cost of 10 now. Your fast Ethernet has a cost of 100. Your slow Ethernet has a cost of 1,000, and your really slow lines have these astronomical costs, which would be kind of appropriate. So you can also do that in a couple of different ways. So let's look at a little bit more in depth on this. You can see its cost also in your show IP route. You can see it in your show IP OSPF interface. So say, for example, you've adjusted your cost to fix to make gigabit Ethernet normal, or your denominator, your standard divisor. Suddenly your cost for this serial interface goes from being 64 to being 647. You'll see that in your metric in your routing update. You'll see it in the show IP interface serial 000. It's another good command to have in your back pocket. You'll see the cost there, right here. And your metric is here and here and here. Now, you can also change your default bandwidth for these interfaces. So there's a reference bandwidth and default bandwidth. These are two different concepts. Reference bandwidth will tell OSPF how to cost these interfaces in terms of their metrics. You can also set these on the individual interfaces. So now the thing to note here is that when you change these bandwidth command values, you don't actually change the capacity of the interface. The physical bandwidth remains the same. These are used by both EIGRP and OSPF. Your serial links are going to it's going to treat all your serial links as though they are T1 lines. If they're not, say for example they're slower than T1 or significantly faster than T1, you may have to adjust that, like so. And we'll go to the next screen. So say for example you do a bandwidth of 64. Now this is the bandwidth command here is kilobits per second. It may or may not have anything to do with your clock rate command. So your auto reference bandwidth is in megabits per second. Your bandwidth command is in kilobits per second. Big difference. So if you want R2 to have a bandwidth, so if you want this 0001 to actually run as though it were a DS0 64 kilobit line, you set that there. If you want to treat this S00 as though it were a true T1 line, you can more or less leave it alone because that's what it's going to treat it as. Say, for example, you want to go halfway in the middle. A single megabit per second. You could set that to 1024 kilobits per second, which is 1 megabit per second. So slower than T1, but faster than BRI. So now, what this does, of course, as I said, is it modifies how OSPF costs that interface in terms of its metric. It does not actually change the length of the bandwidth, the bandwidth of that link. But there should ideally be a relationship between the actual serviceable bandwidths on that link and the way you cost it in OSPF, unless you're trying to seriously tell OSPF not to use something, to make it the route of last resort. Not the route of last resort, because that has a very specific meaning. If you want to make sure that this route is used last, you might tune it down lower than its actual bandwidth in practice. But really and truly, you should probably there should be a meaningful relationship between the bandwidth you tell that this thing that the bandwidth on this link and the cost that OSPF is assigning to it, because you don't want to discombobulate OSPF that much. You want OSPF to be using your network the way the rest of your network is behaving. Now we can set that cost. Now there's one other way to do this. You can set the cost manually. So you can adjust reference bandwidth. You can set interface bandwidth. Finally, you can set your costs with the IP OSPF cost command. So if you take the bandwidth out and you put your cost in, now these two statements are more or less equivalent. So bandwidth 0 will more or less equivalently mean IP OSPF cost 15,000. Bandwidth of 1024 will be cost of 974. A bandwidth of 64 again. So you think about how you want to do this. You should be aware of both ways of doing this. And next we're going to talk about some verification commands you can use with OSPF v2 in a single area. So thank you, and I'll be right back.